Salam, peace be upon you. My name is Muhammad Layak Sadiqi, the father of holophase. Pattern is primary. Phi is circular comparability. Only relations delta phi are public. All material assumptions must be declared. Every claim must declare its type. Pattern, claim, certificate, artifact are four distinct identities. Every claim comes through a declared window. The first thing we read through any window is difference. Structured contrast, not absolute values. Lifts, branch cuts, and the first carrier A. A rigorously simple account of how circular values become locally readable and why the tools we use are not the patterns they reveal. The moment we want to read change, not just difference. Let us pause and feel the weight of where we stand. We have built a foundation of astonishing depth. We learned that pattern is primary, not decoration, but the structure of public reality itself. We named the primitive, phi, the root permission for distinction. Not a thing, but the possibility that this could differ from that. We gave phi its essential shape, a circle. No privileged zero, no absolute origin, only relations matter. We drew the consequence. Absolute values are not public, only relations, differences, rates, loop residues can be shared and certified. We installed anti-smuggling. All material assumptions must be declared. We installed type discipline. Every claim must declare its kind. We installed fourfold identity. Pattern, claim, certificate, and artifact are distinct. We installed windows. Every claim comes from a declared finite access. We then took the first step into actual pattern reading. Difference, delta phi. The first thing we see through any window is structured contrast. Here versus there, now versus then. Now we want to go further. Difference tells us that 2 points have different phi values. But what about the rate at which phi changes as we move from one point to the next? What about the smoothness of variation? What about the local shape of the pattern, whether it is rising steeply or gently, whether it curves one way or another? To read these things, we need more than discrete differences. We need something like differentiation, the mathematical tool for reading local change. But there is a problem. Phi lives on a circle. You cannot differentiate a circle-valued function in the ordinary way without making a choice of where to cut the circle and unwrap it onto a line. That choice introduces ambiguity. And ambiguity, if undeclared, is smuggling. So part 8 asks, how do we read local change when values live on a circle? How do we differentiate without pretending the circle is a line? How do we handle the necessary ambiguity honestly? The answer is we use lifts, local unwrappings that make differentiation possible while remembering that the unwrapping is a tool, not the truth. And we introduce the first carrier of local change. A equals dphi, which captures how phi varies locally while being blind to absolute offsets. This is subtle, but it is also beautiful, and it is the gateway to all deeper pattern reading. A simple everyday example, the winding road and the map. Imagine a road that winds up a mountain in a spiral. It goes around and around, climbing higher with each loop. Now imagine you want to measure the road's slope, how steep it is at each point. You have a device that measures elevation and distance. But there is a problem. The road loops back on itself in map view. If you look at a flat map, the road appears to cross itself, but in reality, it is at different elevations at the same map point. How do you measure slope without getting confused by the loops? You could unwind the road mentally. Imagine cutting it at some point and laying it out flat. Then you could measure slope along this straightened version. But where you cut matters. Cut in one place and the straightened road starts at a certain point. Cut in another and it starts somewhere else. The absolute position along the straightened road depends on your cut. Yet the slope at any point, the rate of elevation change per distance, does not depend on where you cut. It is invariant under different unwrappings. This is exactly the situation with phi. The circle is like the spiral road. It loops back on itself. To measure local change, like slope, we need to lift it and wrap it locally onto a line. The lift is like the straightened road segment. The choice of lift, where we start unwrapping, is ambiguous. But what survives the ambiguity, what is the same for all lifts, is the local rate of change. That is our first carrier, A. Another example, the clock hand and the passage of time. Consider the hour hand on a clock. It moves continuously around the circle. Its position is an angle, a circle value. Now, imagine you want to know how fast the hand is moving, its angular velocity. You cannot just look at the hand's position at one instant. You need to compare positions at nearby times. But here is the subtlety. When the hand passes 12 o'clock, it jumps from just before 12 to just after 12. In terms of the raw circle value, there is a discontinuity from nearly 360 degrees to nearly 0 degrees. Yet physically, the hand did not jump. It moved smoothly across the 12 o'clock position. The jump is in the representation, not in the reality. To measure angular velocity correctly, you need to unwrap the hand's motion. Treat it as continuously increasing rather than resetting at 12. You need to leave the circle values to align. Different choices of where to unwrap give different absolute angle values, but they all give the same angular velocity. The angular velocity is A, the carrier of local change, invariant under different unwrappings. The circular differentiation problem. Why we cannot just differentiate. Let us state the problem formally, but in plain language. Phi takes values on a circle. That means phi at any point is an angle, a number modulo 2 pi, 360 degrees. 0 degrees and 360 degrees are the same point on the circle. Now, suppose we want to know how phi changes as we move from one point to a nearby point. We want something like rate of change equals phi at point B minus phi at point A divided by distance from A to B. But this difference, phi by B minus phi by A, is ambiguous. Because phi values are angles, the difference could be, say, 10 degrees or 370 degrees or minus 350 degrees, depending on which way we go around the circle. The physical reality, the actual pattern, has a definite local change, but the raw circle values do not directly give it. They give multiple possibilities. This is not a defect of reality, it is a feature of circular comparability. It tells us that absolute labels are not the pattern. The pattern is in the relations, not the labels. To read local change, we need to choose a local lift, a way of unwrapping the circle onto a line in a small neighborhood, so the differences become unambiguous. What a lift is: local unwrapping. A lift is a local representation of phi as a linear value, a number on a line rather than an angle on a circle. We write it as phi tilde. The tilde reminds us this is a lifted version, not the original circle value. In a small neighborhood, a tiny patch of our window, we can choose to represent phi as if it were linear. We pick a reference point and unwrap the circle around it so that values near that point increase continuously without wrapping around. This is like taking a small segment of the clock face and pretending it is a straight line. Locally, it works. The circle is approximately linear over small enough distances. The lift font is a tool for legibility, not the pattern itself. It is a representation choice that makes local change readable. Different lifts are possible. You could start unwrapping at a different point or unwrap in the opposite direction. These give different faux values. But the local rate of change, how fast faux varies as you move, is the same for all lifts, because adding a constant or flipping sign does not change the derivative. 6. Lift non-uniqueness, the 2 pi n ambiguity. Lifts are not unique. They are related by 4-4 plus 2 pi n. That is, you can add any integer multiple of 2 pi, a full circle, and get another valid lift. Why? Because if you unwrap starting at a different point, the values are shifted by a constant. If you unwrap going the other way around the circle, the values are shifted by a half circle plus a sign change. This ambiguity is not an error. It is a structural feature that reflects the circular nature of primitive comparability. The key insight: only what survives this ambiguity, what is invariant under phi no d phi no plus 2 pi n, is public phi pattern structure. The lifts themselves are instruments. The public content is what all instruments agree on, despite their different 0 points. 7. Branch cuts, honest seams where unwrapping fails. Sometimes you cannot unwrap the whole pattern consistently. The circle forces a choice. Somewhere you have to cut. Imagine trying to unwrap an entire clock face onto a line. You could cut at 12 o'clock and lay the circle out flat from 12 to 12. But then, at the cut, values that are physically adjacent, just before 12 and just after 12, end up far apart on the line. That cut is a branch cut, a declared seam where the representation jumps. Branch cuts are not failures. They're honest declarations of where local readability requires a choice. In pattern reading, when we use lifts, we must declare where we place our branch cuts. These are the seams where our representation jumps, and we acknowledge that jump rather than pretending the pattern is smooth across it. Hiding branch cuts is smuggling. It pretends the representation is seamless when it is not. Declaring branch cuts is honesty. Here, my representation has a seam. The pattern itself may be smooth, but my reading of it requires this cut. Introducing the first carrier, A equals DFA. Now we come to the most important new concept in Part 8. From a local lift phi, we can form its differential, A equals DFA, pronounced A equals D phi tilde. This is the first carrier of local phi pattern change. What is A? It is the local rate of change of phi. It tells you at each point and in each direction how fast the lifted value is changing. But because phi is a lift, a local unwrapping, A inherits a crucial property. It is invariant under the lift ambiguity. Adding a constant to phi does not change d phi. Changing the lift by 2 pi n does not change d phi. So A is public in a way that phi itself is not. A survives the ambiguity of lifts. It is what different lifts agree on. A is not the pattern itself. It is the first readable expression of local pattern structure, how the pattern changes locally without dependence on absolute labels. Think of A as the local slope, the local rate, the local flow. It captures variation while being blind to offsets. What A is and is not. Let us be very clear about what A is and is not. A is not the pattern itself. The pattern is phi, the circle-valued structure. A is a derived quantity, a way of reading local change. A is not absolute. A depends on the lift, but only in ways that survive the lift ambiguity. It is as absolute as anything can be in a relational world. A is the first carrier. It carries information about local change. From A, we can build higher order structures, curvature, torsion, and eventually geometry and dynamics. A is blind to absolute offsets. If you shift all 5 values by a constant, A does not change. This is exactly what we want for public content. A is local. It tells you about change in infinitesimal neighborhoods. Global structure requires stitching local A's together, part 12. In equations, A equals d phi. In words, the local rate of change of a lifted representation. 10. An example across scales, the river's flow. Consider a river flowing through a landscape. The river's path is a curve in space. At each point, the river has a direction, which way it is flowing, and a speed, how fast it is moving. Now, the river's absolute position, its coordinates, depends on your coordinate system. But the direction and speed at each point, the local flow, do not depend on absolute coordinates. They are invariant under translations and rotations of your map. The local flow is like A. It captures how the river changes locally, where it is going, how fast, without depending on where you put the origin of your coordinate system. If you shift your map, the coordinates change, but the flow vectors, direction and speed, remain the same. The flow is lift invariant. Now, the river itself is the pattern. The flow is A, the first carrier of how the river changes. Another example, the temperature gradient. Imagine a room with a heater in one corner. The temperature varies across the room, warmer near the heater, cooler far away. At each point, you can measure the temperature. But the absolute temperature depends on your scale, Celsius or Fahrenheit, different 0 points. What does not depend on your scale is the temperature gradient, how quickly temperature changes as you move in different directions. The gradient is the same whether you measure in Celsius or Fahrenheit. The gradient is like A. It captures local variation without depending on absolute values. The temperature pattern is phi. The gradient is d phi, the local carrier of change. Lift invariant publicness, the deep principle. Now we can state the principle that organizes all of part 8. Lifts are instruments. Public content lives in what survives lift ambiguity. This means the specific lift phi you choose is a tool, not the pattern. What matters is what all lawful lifts agree on, the lift invariant structure. The first such invariant is A equals d phi, the local carrier of change. Branch cuts must be declared wherever global lifts are impossible. This principle is the local version of the gauge relational principle from part 4. There, we learned that absolute phi is not public. Only relations survive global shifts. Here, we learned that local lifts are not public. Only what survives lift ambiguity is public. The pattern is always what survives transformation. Lifts are transformations. Invariants are the pattern. The rigor layer, the local lift gate. Local lifts get their own gate, the local lift gate. The local lift gate asks, is the local lift declared? Are branch cuts, if any, declared? And is the public claim based on lift invariant structure, especially A, rather than on the lift choice itself? If the answer is no, if the lift is hidden, if branch cuts are smuggled, if the claim depends on the specific lift rather than invariance, the claim cannot be certified. The local lift gate requires declaration of the lift choice if material to the claim, declaration of any branch cuts used, specification of the local domain where the lift is valid, Demonstration that the claim is based on lift invariant structure, like A, rather than on the arbitrary lift values. This gate ensures that local differentiation is done honestly. Firewalls. What lift discipline blocks? Lift discipline installs several critical firewalls. Firewall 1. No treating lift as global truth. A lift is a local tool, not a global representation. Claims that treat a particular lift as the real fee are smuggling. Firewall 2. No hiding branch cuts. Branch cuts must be declared. Hidden cuts pretend continuity where representation jumps. Firewall 3. No conflating carrier A with pattern. A is how the pattern changes, not the pattern itself. Claims that treat A as the pattern are missing the deeper structure. No differentiating across illegal seams. You cannot differentiate across branch cuts or defect cores without declaring the seam. Differentiating across a cut pretends continuity where representation is discontinuous. No letting lifts become the real pattern. Lifts are reading instruments. The pattern is what all lifts agree on, the invariant structure. Never confuse the map with the territory. These firewalls keep local differentiation honest. What lifts give us? Certification outputs. By the end of Part 8, we have installed several certified outputs. Output 1. Local differential carrier A installed. We now have a way to read local change that respects circularity and is invariant under lift ambiguity. Output 2. Branch cut honesty norm installed. We know that seams must be declared, not hidden. This is a core part of anti-smuggling at the local level. Output 3. Basis for jets and local signatures. With A, we can begin to build layered local descriptions, how phi changes, how the change itself changes, and so on. This is the foundation for Part 9, jets. Output 4. Basis for topology. The behavior of A around loops, whether it integrates to 0 or not, will later give us winding numbers and holonomy, Part 13. Output 5. Understanding that A is carrier, not pattern. We have maintained the essential distinction between the pattern itself and the tools we use to read it. These outputs make possible all deeper local and global pattern reading. 16. Refusal conditions, when a claim cannot be certified. Lift discipline gives us clear refusal conditions. Refuse if a global lift is assumed where obstruction exists. If the pattern has topological obstructions, defects, holes, that prevent global unwrapping, and the claim pretends a global lift is possible, refuse. Refuse if branch cuts are hidden. If the claim uses a lift but does not declare the cuts where the representation jumps, refuse. Refuse if A is treated as a primitive absolute quantity. If the claim presents A as if it were a fundamental substance rather than a derived carrier, refuse. Refuse if lift invariant structure is not distinguished from lift choice. If the claim depends on the specific lift values rather than what all lifts agree on, refuse. Refusal here is not pedantry. It is protecting the distinction between pattern and representation. Why this matters beyond science. Lifts in everyday life. Lifts are not only for mathematics. They are a metaphor for how we understand anything complex. In personal relationships, we often lift others' behavior. We interpret it in a certain way. We unwrap it according to our expectations. But our lift is not their pattern. Different lifts, different interpretations are possible. What matters is what survives different lifts, the invariant structure of their character, their intentions, their history. In politics, we lift events according to our ideology. The same event can be lifted as progress or decline, depending on our starting point. What survives different lifts? The factual structure of what actually happened is the public truth. In science, we lift data according to our models. Different models give different lifts. What survives, the invariant predictions, the robust phenomena, is what we trust. Lifts are tools. The pattern is what survives. The handoff. Why jets come next? We now have A, the first carrier of local change. We can read how phi varies locally, independent of absolute labels and independent of lift choices. But a pattern has more local structure than just its rate of change. It also has curvature, how the rate itself changes. It has higher order variations, subtle details that distinguish one pattern from another that has the same rate at a point. To capture this layered local structure, we need jets, the local fingerprint of a pattern, including value, rate, curvature, and beyond. This is what comes next. Part 9. The local signature of a phi pattern, jets and finite readability. This has been part 8 of the Phi Pattern Science Foundation. The journey continues with part 9, the local signature of a phi pattern, jets and finite readability. Always, peace be upon you.